In chapter 12, we're learning about chi-square hypothesis tests. We've already learned about z-tests, which are for proportions. T-tests are for means. Now, chi-square tests are kind of similar to means, except the data that you're dealing with specifically has to be a count of how many times a category is chosen. So we're learning about one hypothesis test in 12.1. This one is called a goodness of fit test. And a goodness of fit chi-square hypothesis test is testing if a distribution of counts in one categorical variable matches the distribution predicted by a model. All right, and our HO and HA are going to be pretty different than what we've seen before. This time it's going to be a sentence. And for HO specifically, the sentence is going to be about the distribution matching whatever the problem claims. And then your HA is going to be a sentence about the distribution not matching. Right, we have 4 conditions. Some of them are the same, some of them are kind of new. We have our random or representative condition. We have our 10% condition. And then one of the new conditions is the data have to represent the count of how many times a certain category was chosen. And then another new condition is, so again, the data is going to be in counts, and then all of the expected cell counts, these need to all be at least 5. All right, unlike a normal model, which is unimodal and symmetric, you can see from the picture, chi-square models are skewed right. Degrees of freedom is going to be the number of categories that the question has minus 1. And there's a different chi-square model for every degrees of freedom, kind of like in a student's T model. All right, here's the formula for chi-square in red. So chi-square is kind of like a z-score, actual minus predicted, or observed minus expected. But this time you square that difference. Observed minus expected, you square that, then you divide by expected, and then you have to take the sum of all of these calculations for every cell. And you won't actually have to do this. The calculator will do it for you, but that's how it works. All right, so underneath that it says the test statistic, which is chi-square. So it's not going to be T, it's not going to be Z, it's going to be chi-square. It's found by adding all those up. And I'll show you an example on the back. All right, there are no confidence intervals for chi-square. We're only going to be doing hypothesis tests. We're going to do 3 for chi-square. Only one of them is in 12.1. So we're learning a goodness of fit in 12.1, and we'll learn the other 2 later in the chapter. Chi-square tests are always one-sided, so there are no two-tailed tests. So we're always just going to be testing if the chi-square value is too large. If the chi-square value is large enough, that will make the p-value small. And if the p-value is small, we will reject the null hypothesis. Our example on the back is asking if births are evenly distributed across the days of the week. All right, so we have a table, and they don't use the word specifically here, but these are observed numbers of births. And so what we want to do is compare that to the expected number of births. And so because they say evenly distributed, that just implies that every day would be the same number. And so because there are 140 values total, and there's 7 days of the week, and we want to know if they're evenly distributed, all of our expected values would be 20. Now, the expected number will not always be the same for every single category. So, for example, if I claimed that 10% of babies were born on Monday, 10% Tuesday, 10% Wednesday, 10% Thursday, 10% Friday, and then 25% Saturday and 25% Sunday, then I would have to take those percentages and multiply by the total. And then, so my expected would look something like 14 for Monday through Friday, since that's 10% of 140. And then, well, what's 25% of 140? 35. Then I'd have 35 on Saturday, 35 on Sunday. So again, it's not always going to be the same. It just depends on what's being asked in the problem. All right, so we learned the term residual a while ago. Residual is actual minus predicted, or observed minus expected. All right, so you won't have to do this work. This is just showing you how chi-square works. So the residual for Sunday would be 13 minus 20, negative 7. Next one would be 3. 24 minus 20 is 4. This one, they were equal, so difference is 0. 7, negative 2, negative 5. All right, then what the calculator does quickly, and you won't have to do this, but the calculator figures out what the residual squared is. So we have 49, 9, 16, 0, 49, 4, and 25. All right, and so the way chi-square is calculated, you take those values and you divide by the expected. So because all of our expected numbers are 20, we're going to be dividing the last row of numbers that we wrote by 20. So 49 divided by 20 is 2.45. 9 divided by 20 is 0.45. 16 over 20 is 0.8. 0 over 20. 49 over 20 again. 4 over 20 is 0.2. And 25 divided by 20 is 1.25. So again, in red, you won't ever have to do this really. This is just so we understand how it works. And so those bigger values that you see for chi-square, that's caused when observed and expected are far apart. And when observed and expected are equal, like on Wednesday, then you have no value for chi-square. So what causes chi-square to be large is when observed and expected are kind of far apart. All right, so let's go ahead and start the process. So we start with our hypotheses. Remember, your HO is a sentence about the distribution, matching. So if we read the question, they ask if local births are not equally likely on all days of the week. Now, when they include the word not, that implies that it does not match. So that would actually be our HA. So then our HO would be that local births are equally likely. On all days of the week. And then our HA would be the opposite. Local births are not equally likely. On all days of the week. All right, after our hypotheses, we do our conditions. It doesn't matter what order we check these in as long as we hit them all. So they do mention it was a random sample. All right, so I'm going to say the sample was randomly selected. And now I'll do the 10% condition next. The sample is less than 10% of the population. All right, and then two of our new conditions. To make it chi-square, the data has to represent a count. And so what is our data? Our data represents a count of how many people were born on each day of the week. So we can say the data are in counts. And then for our sample to be large enough, our sample has to just be big enough to make all expected cell counts at least 5. Our expected cell counts were all 20, so that condition is satisfied. All expected cell counts are at least 5. And remember, this is for expected. It is okay if your observed cell counts are below 5. All right, so we have our 4 conditions. Now we say, since the conditions were met, all right, so the model we're going to use is a chi-square model. All right, so chi kind of looks like a x, but one part of the x is straight and the other part of the x is kind of curvy. Chi-square model, and then you have to say which one. So how many categories were there? There were 7 days of the week, so we had 7 categories. So our degrees of freedom is 6. 7 minus 1. All right, so we're going to do a chi-square model with 6 degrees of freedom. And then, kind of redundant, but I'm going to say chi-square again. And the name of the test we're going to do is a chi-square goodness of fit test. All right, so now let's go to the calculator. Go ahead and put these observed values in L1, and then put the expected values in L2. I recommend you pause the video now while you do that. All right, and then once you've entered in the data, you're gonna go to Stat, Tests, and it's letter D, chi-square GOF, which stands for goodness of fit. All right, so the calculator tells you that chi-square equals 7.6. And then notice that if you add all of these together, again, you won't have to find these individual values for a hypothesis test. Multiple choice might make you do it, but you don't have to find these individual values that I circled on the hypothesis test. You just need the total, which the calculator gives you. All right, so chi-square was 7.6. The p-value was equal to 0.2689. All right, we weren't given a significance level, so we'll use 0.05. Since the p-value is greater than 0.05, remember small p we reject, large P we fail to reject. We fail to reject HO. When you reject, there is evidence of HA. When you fail to reject, there is not evidence of HA. So we conclude there is not sufficient evidence that, and then we have to state HA, but in context. Local births, and I guess our HA actually was already in context because it wasn't an equation like we used to have. There's not sufficient evidence that local births are not equally likely on all days of the week. All right, that last sentence has a double negative, and I have mentioned before, you're not allowed to fix it. All right, that is it for 12.1.